Welcome to our exploration of decision trees and search algorithms. These topics are fundamental in artificial intelligence and typically appear early in most AI courses. Today, we'll take a practical approach, briefly looking at what trees are and then diving into various problem-solving and search techniques using a real-world example. A tree is a nonlinear data structure, consisting of nodes, sometimes called vertices, and edges, sometimes called branches. Each node in the tree can be connected to many children, depending on the type of tree, but must be connected to exactly one parent. The only exception is the root node, which has no parent. In artificial intelligence, decision trees can have thousands of nodes and connections. The complexity of a tree is often measured by the formula Tc equals b to the power d, where b is the branching factor and d is the depth of the tree. Tree searches can be divided into two main categories. Uninformed searches, where we have no information beyond the next decision point. And informed searches, where we have full access to the problem space. Under uninformed searches, we have depth-first search, DFS, breadth-first search, BFS, and uniform cost search, UCS. For informed searches, we will look at greedy search and A-star search. Each of these algorithms has its strengths and weaknesses, which we will explore in detail. And then there is the decision tree on the right for buying a boat. This decision tree is part of a whole folder we have of engineering jokes. The truth is, we still haven't found a person who has never bought anything using this tree. Now, let's get serious again and dive into the core of our topic. To demonstrate these search algorithms, let's use a practical example. Imagine we have a delivery company in Milan, Italy. A customer calls us one afternoon for help with an urgent package delivery. They need this package delivered from their office in Milan to an address in Naples as soon as possible. Our goal here is to find the shortest route for this delivery. Let's start with depth-first search, or DFS. This algorithm explores as far as possible along each branch before backtracking. Let's see how it works on our package delivery problem. We start at Milan, our root node. DFS will always choose to go deeper when possible, so let's follow the leftmost path first. Milan to Turin, 120 kilometers, Turin to Genoa, 100 kilometers, Genoa to Pisa, 150 kilometers, Pisa to Rome, 290 kilometers, Rome to Naples, 190 kilometers. We've reached Naples. Let's sum up this path. 120 plus 100 plus 150 plus 290 plus 190 equals 850 kilometers. This is our first complete path, but it may not be the shortest. Now, we backtrack to the last decision point, which was Genoa. From Genoa, we take the next left path, which is obviously to the right of our latest path. Genoa to Bologna, 200 kilometers, Bologna to Florence, 80 kilometers, Florence to Rome, 250 kilometers, Rome to Naples, 190 kilometers. This new path totals 120 plus 100 plus 200 plus 80 plus 250 plus 190 equals 940 kilometers. We continue this process, always going as deep as possible before backtracking. After several iterations, we discover that the shortest path found so far by DFS is 740 kilometers, going through Milan, to Genoa, to Pisa, to Rome, and from there to Naples. Note that so far we have calculated only the left-hand side of the tree, and there's still work to do to complete the search. But we will stop here, because the principle behind DFS is clear. So what are the advantages of depth-first search? First, DFS requires very little memory. It only needs to store the nodes on the current path. Also, it can reach a first solution quite fast even if the solution is located deep in the tree. As for the disadvantages. First, it is not guaranteed to find the shortest path on the first go. In our case, it found a 740 kilometers path, but we don't know if it's optimal without completing the search, which we haven't. Second, DFS may get stuck in an infinite loop if the depth of the search tree is unlimited. Let us now explore breadth-first search, BFS. Unlike depth-first search, breadth-first search explores all the nodes at the present depth before moving to the nodes at the next depth level. We start from Milan, and explore all its immediate neighbors. Milan to Turin, 120 kilometers, Milan to Genoa, 110 kilometers, Milan to Bologna, 220 kilometers, Milan to Verona, 140 kilometers. Now, we explore the neighbors of these cities, always completing one level before moving to the next. Level 2. Turin to Genoa, 100 kilometers, total so far, 220 kilometers, Genoa to Pisa, 150 kilometers, total so far, 260 kilometers, Genoa to Bologna, 200 kilometers, total so far, 310 kilometers, Bologna to Florence, 70 kilometers, total so far, 290 kilometers. Bologna to Ancona, 200 kilometers, total so far, 420 kilometers. Verona to Bologna, 130 kilometers, total so far, 270 kilometers. We continue this process, level by level. At each level, we keep track of the cumulative distance from Milan. If we reach Naples, we mark it but continue exploring the current level. This methodical, level-by-level approach ensures that if there's a path to Naples, we'll find it, and it will be the shortest. So what are the advantages of breadth-first search? First, BFS will always find a solution if one exists. Also, if a solution exists, it will always find the least cost one. The disadvantages are: first of all, it requires a lot of memory, as it needs to store all nodes at the current level. Second, it can be slow if the solution is far from the root, as it explores all nodes at each level. Uniform Cost Search, UCS, is similar to BFS, but instead of exploring all the nodes at every level, it goes for the node with the lowest cumulative cost, which in our case is the distance traveled since we started our journey. This makes it more suitable for graphs with varying edge costs, as in our case. So we start from Milan, and calculate the cost to reach each of the cities on level 1. We choose the lowest cost, which is Milan to Genoa, at 110 kilometers. We are done with level 1 and our next goal is level 2. Now, we need to calculate all of the combinations that get us all the way from Milan, to any one of the cities listed in level 2 of the tree. We now see, that although driving from Milan to Genoa was the best choice for the first leg, when also the next leg is factored in, the lowest cumulative cost is the one passing through Turin and Genoa. So we immediately switch routes to that choice, which is our best so far. It is marked in purple on the tree. Now, everything is open again for a fresh evaluation, and we are looking to find which are the 3 first legs, that have a minimum total driving distance, all the way from Milan to one of the cities at level 3 of the tree. Again, looking at the numbers, we find that we have a better result if we switch to a different route. The new best choice is the one from Milan to Genoa, then to Pisa and from Pisa to Florence, marked in green on the tree. This repeats itself going down, level by level, until we reach our target. Of course, this search must be completed before embarking on our trip, because there is no way to tell what our first move is, until we have reached Naples in our search. And once we have reached Naples, we have our best route according to UCS. So what are the advantages and disadvantages of UCS? There's one advantage, which is that UCS always finds the optimal solution, and does not waste time on expensive paths. The main disadvantage is that it can be stuck in an infinite loop. Next is the greedy search algorithm. Greedy search introduces the concept of a heuristic estimate, h, of the anticipated cost from the current node to the goal. In our case, we'll use the straight line distance to Naples as our heuristic function h of n. Note that we have now moved from blind searches to an informed search, where we have the full map of Italy at our disposal, and not just a list of cities and the distances between them. We start from Milan and calculate h of for each neighbor. Milan to Turin, h of Turin equals 720 kilometers, Milan to Genoa, h of Genoa equals 580 kilometers, Milan to Verona, h of Verona equals 600 kilometers, Milan to Bologna, h of Bologna equals 430 kilometers. So we choose the lowest h distance, Bologna. From Bologna, we calculate h of n for the candidates of next leg of the journey. These are Ancona and Florence. Bologna to Ancona, h of Ancona equals 310 kilometers, Bologna to Florence, h of Florence equals 420 kilometers. Ancona is the lower cost, so we choose Ancona. From Ancona we have two possibilities. Ancona to Pescara, h of Pescara equals 160 kilometers, Ancona to Rome, h of Rome equals 170 kilometers. So we choose to go through Pescara, and from there, we need to decide between Foggia and Rome, as there is no highway from Pescara directly to Naples. Foggia to Naples equals 110 kilometers, Rome to Naples equals 170 kilometers. So the choice of course falls on Foggia. The final route is therefore, Milan to Bologna, Bologna to Ancona, from there to Pescara and then to Naples through Foggia. The total driving distance is 220 plus 200 plus 90 plus 150 plus 110, equals 770 kilometers. Here are the advantages and disadvantages of the greedy search method. Advantages: very fast and minimal memory requirements. Disadvantage: does not always find the best solution, as it can be led astray by the heuristic. Finally, the A-star search algorithm. This famous algorithm combines the actual cost to reach a node, g of n, with the heuristic estimated cost from that node to the target, h of n. It defines a function f as the sum of g of n and h of n. So let's start calculating. Starting from Milan we have Milan to Turin, f of n is 120 plus 720, equals 840. Milan to Genoa, f of n is 110 plus 580, equals 690. Milan to Bologna, f of n is 220 plus 430, equals 650. Milan to Verona, f of n is 140 plus 600, equals 740. We choose Bologna as it has the lowest f of n. From Bologna we have Bologna to Genoa, f of n is 220 plus 200 plus 580, equals 1000. Bologna to Florence, f of n is 220 plus 70 plus 420, equals 710. Bologna to Ancona, f of n is 220 plus 200 plus 310, equals 730. So we choose Florence, and from there, all that remains is to drive to Naples via Rome. The total driving distance is 220 plus 80 plus 250 plus 190, equals 740 kilometers. Here are the advantages and disadvantages of the A-star algorithm. Advantages: the A-star algorithm is considered the best overall performer of all search methods, as long as good heuristics can be found. With a good heuristic function it can solve very complex problems. The disadvantages are, first, it does not guarantee the best solution, and second, it can still require a lot of memory for complex problems. Still, worth mentioning, when NASA had to decide on a way to help Opportunity, their current Mars exploration rover, to avoid large boulders and sand dunes, it chose the A-star algorithm over others. We should mention here that there are also other tree search algorithms that we didn't cover here. One of the more successful one is Monte Carlo. We may have a separate video on that algorithm in the future. To sum up, as we've seen, each search algorithm has its unique approach to exploring the search space. DFS goes deep quickly but may miss optimal solutions. BFS ensures the shallowest solution but can be memory intensive. UCS finds the optimal path but may explore unnecessary nodes. Greedy search is fast but can be suboptimal. The A-star algorithm often provides the best balance, combining actual path costs with estimated future costs to guide its search efficiently. The choice of algorithm depends on the specific problem, the structure of the search space, and the available information. In practice, the A-star algorithm is widely used in pathfinding and graph traversal due to its balance of efficiency and optimality, but each algorithm has its place in the toolkit of AI and computer science. Finally, here's a visual illustration demonstrating how different search tactics are relative to others.